Welcome to class meeting 21 of the Introduction to Optimization. We have second exam and the fourth homework due today. So let's do some review. This is the set of all constrained optimization problems. And this is the topic of the kind of last half of this course. One of the important subset of this universal set is the set of convex optimization problems. And it is defined as the minimization of a convex function f on the convex constraint set omega sub e explicit constraint intersected with the implicit constraint set. Okay? So you can say that the general convex optimization problem has the form of minimization of convex objective function on a convex constraint set. And there is another important subset in this universal set of all constrained optimization problems is the subset of constrained optimization problems with equality and inequality constraint functions. So it looks like this. We want to minimize an objective function f subject to first this g vector value, the function of x is called the inequality constraint function, or you may say that each component of this g vector value, the function is the inequality constraint functions, and here h also the vector valued constraint function now is called the equality constraint function. So this is a kind of subset of constraint optimization problems. Be careful, there may exist other type of constraint optimization problems. Non-convex and the constraint set explicit one is not described by equality and inequality constraint. So this is a subset. Now we have intersection of these two. So I have to say that this is not the entire one. Just a second. Should be careful. So here is another subset. Okay, convex optimization in a narrow sense. Okay, so this narrow sense has some strange thing. Here, this f is a convex function. This g, that is the inequality constraint function, is also a convex function. And now, since this is a subset of this set, we need some equality constraint function. Here, we have what? Affine equality constraint function. Got it? And in the convex optimization theory, you can easily show that if g vector valued function is a convex function, that intersected with this ax equals b equality constraint function always give you a convex constraint, explicit constraint set, feasible set. Got it? So this g is convex and equality constraint function is ax minus b. It guarantees that this is the convex. Okay? Of course, there may exist some other constraint, other convex optimization problems with equality and inequality constraint functions without having this affine inequality constraint function. But if you look at the convex optimization theory, this form is called the standard convex optimization problem. Got it? So linear programming we are currently studying is what? So linear programming in the standard form looks like this. We want to minimize C transpose X subject to AX equals B with B strictly negative and X X B non-negative and X non-negative. Okay. So if you compare these two shapes, okay, see that C transpose X, that is a hyperplane, is actually convex and at the same time concave. So this is okay. Now let's see the inequality constraint. And this what? Here you say that g of x is minus identity of times x, right? So no problem. And ax equals b is here. So you can easily see that this linear programming in the standard form, standard LP, is what? Is this convex optimization problem in a narrow sense. In a narrow sense. This is kind of convex optimization problem in a wide sense. Got it? So anyway, we are here. By the way, general linear programming problem has a affine objective function and equality and inequality constraint functions that are both affine. So we have to show that any linear programming problem can be converted to a standard LP problem. And we studied that by introducing slack variables, surplus variables, and sometimes free variables. Sometimes we just negate the sign, blah, blah, blah. Got it? And after that, we studied basic solutions and basic feasible solutions. The basic solutions are solutions in this form. Suppose you are given the equality constraint functions. Here we assume that B is in the range of the matrix A, and A is an n by n matrix with m less than n, and rank of A equals m. That is our assumption, and also this is also assumed. So basic solution is related with equality constraint only. And what we do is that we choose m columns out of total n columns of A. For example, this is an augmented matrix with A here and B here. What we do is that we choose m columns from n columns. And then only using those m columns, we want to rewrite B. So, for example, if we choose first m columns, the idea is this. We want to find a vector x such that this is true. So in this case, in this example, we have chosen first m columns. To find such x, we apply elementary row operations to what? To this equation. That corresponds to what? That corresponds to pre-multiply a matrix to this augmented matrix. For example, suppose there are some elementary row operations applied to diagonalize the first m of that, then what do we have? We have something like this. And here we have some columns, m plus 1, m plus 2, n. And here we have, let's say that is y0. Okay. This is a notation. Be careful. This is a simple notation. Okay. So there is a corresponding system of linear equations in terms of x1 through xn. Got it? So by doing such a law operations, we can easily find the basic solution. Okay. There are at most n choose m basic solutions. At most, okay. Unless there is some strange case with uncountable infinite number of solutions. But anyway, so these are basic solutions, and basic feasible solutions are basic solutions that are feasible. Okay, so this is BS, and this is basic solution, and the elements are all non-negative. And the fundamental theorem, linear programming, says this. It's an existence theorem. Actually, it consists of two existence theorems. So you may say that fundamental theorems of linear programming. First one is that if the constraint set is not an empty set, then there exists a basic feasible solution. Second, if there exists an optimal solution, then there exists an optimal basic feasible solution. So the implication is that somehow if we can show the existence of the solution, then what? We just need to take a look at those basic feasible solutions to find an optimal solution. Anyway, so this is the idea, and what we do is like this. We study an algorithm called simplex algorithm or simplex method to solve a standard form linear programming problem, where we just start. So this is step one. Start with a basic feasible solution, and then in step two, we move to another basic feasible solution. Just a second. Yeah. That has a lower objective function value. And we keep doing this until stop at a stopping criterion is met. So simplex method looks like this. Looks very simple, but each step has some problem. First, how can we find the basic feasible solution? And you may say that number of basic feasible solutions in many cases will be just n choose m. It may be small, it may be large. We've seen that when n is 50 and m is 5, number of basic solutions is around billion. It may be large or it may be small. Anyway, so we have some doubt about how to find a basic feasible solution. In the second step, when we move to another basic feasible solution, how do we move? Right? So we just randomly choose some other set of columns of A. We may do that, but in that case, it's not a systematic way of such, right? We may do this, for example, we start from basic feasible solution, which means that we have a basic feasible solution and we have the objective function evaluated at that solution, right? Now, that is, for example, is a basic feasible solution corresponds to A1 through AM. Now, we want to move to another basic feasible solution. So, for example, we randomly select, for example, M columns out of N. And if this set is not consisting of 1 through M, then we may try to find the basic solution and check whether that solution is feasible. And then what? We evaluate the post function, objective function, and if it decreases the objective function value, we may move. But if we do some such random search, if the number of basic feasible solutions is small, then it seems it's not a good idea. Right? So somehow, again in the second step, how systematically we can do that? And third, after we, if for example, suppose we have done step 1 and 2 and we evaluate the objective function value and we have decreased, it's okay. But what kind of stopping criteria? So, suppose we've done random search and here we may not know whether we have to perform such random search further or not. Right? So even though I said simplex method consists of 3 steps, all 3 steps are currently questionable. How? Right? So if I follow the historic development of this idea, it may take too long. So the textbook kind of attacks this second step first. Temporarily saying that, okay, suppose step 1 is done somehow. Got it? And surprisingly, step 1 is a kind of special case of step 2, it turns out. So anyway, learning step 2 kind of simplifies all the understanding. So we are going to start from step 2. Got it? So step 2 assumes what? Assumes we already have a basic feasible solution. What does this mean? Basic feasible solution. It is a basic solution, so we already have chosen some M columns, and what? That X has what? All non-negative values. In such case, what we do is like this. Without loss of generality, this is a kind of very popular acronym, not used in journal papers, but mostly used in classes. Okay, this is without loss of generality. Okay, let's assume A1 through AN. The first M columns are those columns chosen for that basic feasible solution. We can assume that. What does this mean? What does this mean? Using the augmented matrix. What does this mean? This means that from the original augmented matrix, we have multiplied a sequence of matrices that corresponds to elementary row operations. And altogether, we can say that that is some matrix something. Okay? We have converted this one, that is equivalent to, for simplicity, we say B, D, and B, somehow identity, and some columns, and Y0. Actually, elementary row operation to just corresponding to the first M columns, this is M by M identity matrix, okay, just says this one. This is equivalent to X1 plus, sorry, not this one. Suppose X can be written as XB, XD. So, first M entries of X is denoted by XB, and the rest of them denoted by XD. Then what does this mean? IM times XB plus Y times XD equals Y0. Am I right? Am I right? So you have to kind of cut here and put this together as a matrix and multiply X to find Y0. So you have IM Y XB XD equals Y0. Okay? That's why you have this. Now, how do we find a basic feasible solution from this set of equations? We just said XD equals 0. And what happens? XB is chosen as Y0. Got it? So that is assumed already done. What does that mean here? The key is that we assume this one has all non-negative components, because we assume this is a basic feasible solution. Got it? By the way, to develop the idea of simplex method, we may use some general linear programming, but here we intentionally use the standard form because that's very useful. Okay? And similarly, in the standard form, what we have, AX equals B with B all non-negative. Again here, assumption of feasibility says that Y0 has all non-negative components. Okay? So in the first step, suppose we have this. Now, we want to move to another basic feasible solution, right? Among moving to another basic feasible solution, what is the simplest, straightforward way? What would be? So, to understand that, let's see what is a simplex. When I was an undergraduate student, I didn't search for the meaning of simplex. At that time, there was no Wikipedia, okay? There was no Google, and there was no, how to say that, my intention to look up some elementary geometry. The simplex, if you search for the meaning of this one, it's a generalized version, generalization of a triangle. to a higher dimension. What is a triangle? What is a triangle? Triangle has some three sides. These are called side. Okay. Sometimes, and also this is called vertex, 꼭지점. Okay. This is 면 in Korean, 꼭지점 in Korean. And in simplex, let me give you an example. Let's consider such a constraint set, okay, in three-dimensional space. So X consists of x1, x2, x3. So first one means that what? It's an equality constraint function, right? x1 plus x2 plus x3 is 1. And what about the inequality constraint? They are all non-negative. So if you draw what do you have? You have something like this. And so actually here, this constraint set is a triangle. Be careful, this is 0 and others are not satisfying this one. Okay. You may extend this one to higher dimension, in 4 dimension, billion dimension. In that case, such a generalized triangle is called especially a probability simplex. Okay. So this is the 3D probability simplex in three-dimensional Euclidean space. Unfortunately, we cannot draw a probability simplex in 4-dimensional space. We can't do that because we only think in 3 dimensions. By the way, what is a probability simplex in 2D? What is a probability simplex in 2D? This line segment. Got it? So actually, simplex can be the generalization of triangle to a lower dimension. No problem. And here, the idea of simplex method is like this. Suppose this is your basic feasible solution. And what you do is that when you select next basic feasible solution, when you search for next basic feasible solution, you search for adjacent basic solution and check whether it is feasible or not. So in this case, it is 1, 0, 0, and this is 0, 1, 0, and this is 0, 0, 1. And let's see what's the property of adjacent basic solutions. What's the property? In this case, the third component is 0, right? Third component is 0, and here actually only the second and third is 0. And here, from here to here, what you do is that you choose one column to leave, to be out. In this case, the first column. And among these two, you choose one column to be included in, right? Similarly, the simplest way of search in the step 2 may be you start from a basic feasible solution by the assumption, and you try to find adjacent basic solutions. Which means that you just need to choose one column that is included already now to leave. And another one column, it was originally excluded, but now to be included. So Moving to an adjacent basic solution requires you to choose the pth column to leave and the qth column to come. Okay, so it's like replace the pth column, replace the pth column with the qth column. We need such a step. Now let's take a look at an example, because it's much simpler. Suppose you have chosen first the two columns and have performed already elementary row operations. So that in this case this is a diagonal matrix, right? And this is about the third component x3, and this is y0. So what is a basic feasible solution? Say x0. What is that? 4, 5, 0. Am I right? This times xb plus this times xd, that is x3, but we just ignore x3. Set x3 is 0. So we have this, right? So it's a basic feasible solution. Now, among these two, you choose which one to leave. But in this case, there is only one, so this comes in, right? So say you choose second one. So second out, third in. Let's consider this case. Now, what do? You may start from the original augmented matrix AB and just choose first and third column. That is one way, and do elementary row operations. But the question here is that, can we efficiently find a new basic solution given this transformed augmented matrix? Because we've already done this, and this may save a lot of computation time to us. And you already know, okay? So what our objective now is to change this to 1 and change this to 0, and somehow keep this 1 and 0 by doing what? Pre-multiplying some elementary row operation matrices. And it's not that difficult, because we already know this is same as what? x1 plus 0x2 plus 2x3 is 4, and 0x1 plus 1x2 plus 3x3 is 5. So in order to make this one to 1, definitely we multiply 1/3 to the second row here. That corresponds to, we divide this second column by what? This number 3. Right? And what do? So it's like we change this to 1, 0, 2, 4, 0, 1/3, 1, 5. Okay. So it's like second row divided by 3. That's what we've done, right? And now what do? We want to convert this to 0. And what do? Row operation. So we multiply this number to the second column and subtract from the first column. So eventually we have 1, 0, 0, 0, 1/3, 0, 2/3, 5/3. Okay. So here first minus second times 2. And we keep the second one, right? So we've done this. And if we have more rows and more columns, we similarly do this. Right here, interesting thing is this one. The first column that is not chosen to leave is still unchanged, right? Even though we did some row operations. It's kind of obvious if you see that. Because first we divide this column and it's already 0. So it shouldn't be changing, right? And when we multiply 2 to this column and subtract, this is 0. So if we subtract 0, this is 1. Okay. And similarly, even if we have more rows, if we choose pth column to leave, to have qth column in, all the other columns from the that original identity matrix does not change. What only changes is this part and that part in this case. So we generalize this one and call it pivoting. So pivoting is like this. The first step is that, by the way, here we assume that we have already chosen which column is to be replaced by which column. Okay, so the assumption is that choose P and Q such that P out, Q in. Second, what do we do? As we've done here, by the way, in this example, we have this corresponds to P and this corresponds to Q. So here, this corresponds to P, and what is this? What is this one? Pth row, Qth column component. Am I right? And what is this one? In this case, the first row, Qth column, right?
뺐는데 저 마이너스 3분의 2 생기면 안 되나?
Just a second. Let me see. Which one? Which one? This one?
1행 2열에
This one?
네, 그거
Okay. Sorry about that. This should be 1, right?
Yes.
Yeah, and this is still the same.
그 3분의 1 위에
Which one?
3분의 1
Just a second. Let me check. Okay, so 1024, 0135. So we do division, right? So up to this, it's okay, right? Yeah. And in the first, we subtract. Okay, so this is, you mean minus? No. This. Sorry. Yeah, this one. Got it. Okay. Minus 1/3. 2/3. Strange. First times 2/3. Yeah. Now, am I right? Still wrong? Okay. Yeah, it doesn't matter. Anyway, x2 is now to be set 0. So don't care. But anyway, my mistake. Okay. So here, this means that our basic solution is what? So you choose 2/3 for x1, right? And 0 for x2. And 5/3 to x3. And fortunately, this is a feasible solution. Got it? So we've been lucky in this case. But anyway, so let's generalize from this example. So suppose we have chosen P and Q. P out, Q in. Or replace P's column with Q's column. And first, what you do is that, so this is a row and this is, we use this APQ. So Pth row, Qth column, right? So what we do is that we divide the pth row by APQ. So replace the pth row with pth row divided by APQ. Right? That is this first step. And the next one is that replace ith row with what? Ith row minus pth row times AIQ. Right? So in this case, see that the first means ith, right? Here second means pth. And 2 is A1Q, AIQ. Got it? So we do this for all I that is not P. And if we do this, of course, this third sub-step requires m minus 1 operations. But anyway, by doing this, we can find, be careful, we can find in general a basic solution. I haven't yet said it's a basic feasible solution. It's a basic solution. So we don't need to touch any other thing. Okay? We already have E1, E2, those standard basis vectors already, and only one column is leaving, and another column is in and replace the E sub P with new E sub P. Okay? Because P's column left means that the P's column was E sub P, the P's standard basis. Got it? So anyway, such an operation is called pivoting or pivoting operation. And this pivoting operation is, how to say that, is to provide us a way to move from one, in this case, basic feasible solution to adjacent basic feasible solution. You just need to find, choose some PQ, a pair of two columns to be replaced by another. Okay. Now, then question is this. So suppose you have a basic feasible solution. How do you choose P and Q? Right? This steps shows that if you choose P and Q, then there is only one way, okay? One way to find the basic solution. How do you choose P and Q? And also, amazingly, this simplex algorithm has kind of the simplest idea works. See that? As I told you, in the second step of simplex algorithm, we want to move from a basic feasible solution to another basic feasible solution that is better. And this idea actually will work is that we start from a basic feasible solution and search for adjacent basic feasible solution only, right? By using pivoting. And in addition, when we choose P and Q, the simplest idea works. The idea is like this. There are two simple ideas. One is that, first, again, assume we have already chosen P. And the question is how to find Q. Or, suppose we have already chosen Q and try to find P. As a researcher, suppose you are at that time of development of this algorithm, researcher, probably you tried both of them. Okay? And it may be educational to try both of them, but I will not do. Okay? So here the textbook shows that, okay, what if we assume that Q is chosen? Actually, the reason is that that gives us something that works. Okay? Suppose Q is already chosen. And see how to find P. Got it? So this development is kind of very, how to say, tricky. There are many ways to do some such or basic feasible solution. There are many ways to choose the pair P and Q. But among them, possibly the simplest idea actually works and included in the simplex algorithm. So, how to choose P given Q. Okay. So after we study that, we will study how to choose Q. Got it? So now the idea is this one. So we have something like this. And we've already chosen Q that will come. Now, how can we find the pth column to leave? Got it? So that is the task here. We may try one by one, right? Yeah. That is one way. But here the assumption is this one. We assumed we already have a basic feasible solution, which means that y0 has all non-negative value. Am I right? And also, we do not just want to move to a basic solution. We want to move a basic feasible solution. Right? So, this feasible is very important. If we want to move to a basic solution, we may arbitrarily choose, right? So that's not what is listed here. So what do we do? Interesting thing is that from this augmented matrix, we must be able to find P. Now let's see that pivoting again. Okay. So let me write here 1 0 2 4 0 1 3 5. By the way, I want to emphasize this. Probably you are at the early stage of your PhD or master's program. And if you read some research papers, it looks like this, okay? Linear programming, like some there is a called pivot equation, pivot. So let me show you. See that? A sub pj prime equals A sub pj divided by APQ, and Aij prime equals. How can you understand this? Actually, no researcher starts from such an algebraic equation. They start from an example, okay? And then they just write it down using algebraic equation. Never forget this. And also, never be frustrated when you see something like this. Just find a good example with numbers, numeric example. Okay. Actually, this is the first page. Or is it first page? Yeah, first page of your lecture note. Just right here, okay? Pth row, right? Pth row, and here, other than pth row, okay? See, you remember that? Given a canonical matrix, given an augmented matrix, I somehow have set what? The APQ to 1, right? The first step is to choose that row, that example, second row, and divide by APQ. That is this one, okay? So this one is just what? You change the pth row, okay? See that? J runs from 1 to m plus 1. In this case, m, a, only a is involved. And these are all other than pth row, okay? So these are just those two steps, given you've chosen P and Q pair. Got it? So never forget, never be frustrated. Anyway, so in this example, what? We've chosen already that Q's column is to be included. And as you see here, what? Anyway, then x3 will just this divide by this one. Am I right? As you see here. And this should be feasible. So first, what if this is negative? Or 0? You cannot divide. You cannot make it 1, right? If it is 0. If it is a negative number, if you divide this second row with, for example, -3, what you have is -1, so you do not have a feasible solution. So you have chosen, in this case, the third column, already means that APQ is positive. Got it? APQ must be positive. Okay? Which means that when you choose Q, you have to choose P that gives you APQ positive. Okay, got it? So the first step is this. Sorry, I is not P. Right? You have chosen Q already. So you look at the Q's column, right? Am I right? You look at the Q's column of this one. So Q's from here, right? So you look at the Q's column that is already chosen, and you have a vector. And if ith row of the Q's column is negative, they shouldn't be chosen as P, because that will give you infeasible basic solution. Okay, so this is first step. Then what is second one? So this is related to that first pivoting equation, normalization step. And for the second one, what do we have? We have this complicated, apparently complicated looking pivoting equation. And let me show you this one. Okay, here. So this is the pivoting equation. And this is for the matrix A part. What about that B part, Y0 part? Updated Y0 looks like this. This is paired with that one, right? Just normalization. This is paired with that one. And now we want is that this is the P is going to be chosen, and this must be non-negative. Now if you compare these two, it's not just replacing the column number as 0. That is the rightmost one. Got it? And if we take this part out, then we have this formula. And take a look at it. What does that mean? You have already chosen Q, right? You already have chosen Q, the Q's column. Now you want to choose P, the row number. Now what is this one? What is this one? The rightmost column value, right? This is also the rightmost column value. Pth row, ith row. So what you do is that here, if you compare it to 0q, 0q, so what you do is that you change I from, for example, m plus 1 to, let me see, 1 to m, right? Because P is between 1 and M, because that is to be living, right? Now, what does this mean? 1 over I must be chosen P, right? So it's like you have M, this ratio. I figured out. So there are two cases for this one. So here, case 1 is YIQ is negative. What does that mean? If for some I, suppose this is non-negative. Okay, be careful. We have IQ, Y sub Q, that has Y1Q to YMQ. Got it? So we already have chosen this one. And some of the entries are negative. Now see what happens. This is negative, am I right? Right? By assumption, for that I, this is negative. And this is negative. Right? Same number. Now what is this one? By the assumption of basic feasibility of the original one, this is positive. Right? So this is negative. And what about this one? We assume that this is positive and this is positive. We are going to choose some P that makes this positive. So this is negative. So this parenthesis gives us a negative number, and this is negative, so this is positive. Got it? So in this case, it's okay. Always holds. Now, case 2. Suppose this is positive. Then what happens? So among these, we may divide these components into 3. Those negative ones, those positive ones, those zeros. So for those negative ones, such I cannot be P, because we assume that YPQ is positive. Right? So they are just okay, but they are not chosen. For those zeros and negatives, for zeros, we cannot divide, right? Because we cannot do this, right? So for positive ones, what do we do? So suppose that we have Y10, Y1Q, Y20, Y2Q. And consider choosing, for example, the I equals 1 to leave. Then what happens? We have to subtract this from that one. And that should be positive. So this should be smaller. Vice versa, if we choose second column to leave, what should happen? This must be smaller than that one. So among positive ones, we have to choose smallest one. Okay, so here P equals argmin yi0 yiq, such that yiq is positive. That's why here we have this condition. Got it? We are not just find I, then minimize this one. We find I, then minimize this one, and makes this denominator positive. Got it? Okay. So complicated. Anyway, by doing this, we can find a basic feasible solution. Got it? So let me repeat. Okay. in the second step of the simplex algorithm, we want to move from a basic feasible solution to another basic feasible solution. The simplest idea would search for adjacent basic feasible solution. And to search for adjacent basic feasible solution, you have to choose P's column to leave and Q's column to be included. Suppose, it's too good to be true, but suppose after we choose Q, try to find the P that works. And in this case, in this simple algorithm, this is another algorithm, right? We choose Q already and try to find the P. And it seems that we can move to a basic feasible solution if such Q's column exists. Q's column is chosen. Okay. See that here? Be careful. If you want to choose Q's column, that is all negative, non-negative, does not work, right? So you have to choose the Q's column that contains at least one positive number, right? Because APQ must be positive. Anyway, so now how to choose? Before doing that, I need to talk about one more thing. So how to choose Q. So first, anyway, given elementary row operated augmented matrix, we already assume that this is given, right? Because we assume that we start from a basic feasible solution. And here, Y0 has all non-negative numbers without loss of generality. We want to find Q that is greater than or equal to m plus 1 and less than n. So we want to choose one of the column here, right? If we choose column, Q's column, then finding P's column here is easy. We've already done how to do that, right? So we need to examine these columns. And here, there is a kind of side. Okay, it's time's up, but let me little bit talk more. Suppose some YQ, not say YJ, okay, with J between m plus 1 to n has, suppose there exists all negative. Is it all negative? Let me see, just a second. All negative. All non-negative, sorry. Okay. So it's like we examine the columns of Y. And somehow we find, by examining, we find some J's column among these that has all non-negative components. What does that mean? That is stated in page 5. Okay. If you take a look at the lecture note, page 5, the second last bullet says, note, if yiq less than or equal to 0 for all I. What does that mean? There exists a J's column that has all non-negative components, right? So sometimes if you have already familiarized with such notation, okay, this if y, I, q less than 0 for all I, this is kind of cumbersome. Right? You don't need to do it. Okay? Anyway, so you find some column like this, then what does that mean? Then there are feasible points with arbitrarily large components. And actually this is some case like this. Suppose you have something like this as your feasible set. For example, you have two equality constraints and one non-negativity constraint for the linear programming. So this space is what? First quotient, right? Now from this point on x1, x2 plane, this ray may be a feasible solution, the set of the constraint set of your linear programming problem. In that case, what? Arbitrarily large components may be possible, right? By moving that way. Actually, this case is related to that one. Since I've run out of the time, I will explain this on this Wednesday. But anyway, so this is a good example, you remember. Or you'd better draw this one to that second last bullet on page 5. Okay? Sometimes such a simple visualization a lot helps you. Okay. Anyway, today I little bit bumped around by this condition. Okay. But anyway, we've covered up to page 5, and let's quickly see, even though we've already run out of time. So simplest method is related to a simplex. A simplex is a generalization of a triangle. And I've talked about a probability simplex in 2 dimension and 3 dimension. And higher dimension, we cannot figure out what it is. And simplex method is an organized way moving from one basic feasible solution to another basic feasible solution and end up with an optimal basic feasible solution when an optimal solution exists. Got it? And to do that, this is a little bit, the order is twisted, but what is important is that we want to start from a basic feasible solution and move to an adjacent basic feasible solution. And this operation requires what? The pivoting. And pivoting consists of what? 2 equations, but the second one actually consists of what? Consists of m-1 operations. First line is related to normalization, and second line is to make the rows of that Q's column all 0. Okay. So using an augmented matrix, it can be easily understood. And example must be used to derive the pivoting equations. Okay. And you also do when you do your research. Okay. You start from example and just generalize by putting some subscripts. And when you move from one basic feasible solution to another, there are many ways, but we assume that the column to be included is already chosen. And how to choose the column to leave can be easily found by using this algorithm. Got it? So we examine each after we choose Q, we examine Y sub Q vector. And the components of Y sub Q vector are either 0 or negative or positive. Okay. We ignore all negative rows to be chosen as P, but for positive, what do? We somehow calculate this one and find component I that minimizes this one among those making the denominator positive. Got it? And that is how to choose P, and from here it is related to how to find Q, and that will be discussed next time. Okay. Okay, that's all for today.